Okay, so guys, I was going to help you guys out with a couple problems from the latest homework. Homework number 4 for rotational kinetic energy. I know you guys had problems with number 2 and number 10 mostly, so those are the ones I'm going to work out. Before we jump into this though, problem number 2, I wanted to talk about that moment of inertia we talked about. I had some good questions on that. What is moment of inertia? Well, if you remember, when we talked about centripetal acceleration, this object, right? If you look at any one point on it, it's going to have a velocity in this direction, right? Every object, if you remember Newton's law of inertia, his first law, says any object in motion will stay in motion in the same direction with the same speed, right? At the same velocity, unless acted upon by a force. So what you notice though on a wheel is that things don't go in a straight line, even though they want to. They don't. So what is moment of inertia? It is basically the tendency of that little bit of mass that's out here, right? Or here, or wherever, to want to keep going in a straight line. So it actually is basically the tendency of that mass to not want to go in a circle. So you actually have to force it to go in a circle. And the way you do that is using centripetal acceleration, right? By accelerating it towards the middle, that velocity will change from this direction, same speed later on, but it will change direction because it's got an acceleration in this direction, okay? Or vice versa, if you're on the bottom, centripetal acceleration will be this way, even though your velocity on that wheel going like this would have been like this, it'll want to keep changing direction as it goes around, okay? So your moment of inertia is basically your ability of that mass to resist going in a circle. So you have to force it, okay? You have to force it using torque or acceleration. So that's why you have to plug this thing into your formula for rotational kinetic energies, because it takes energy to basically maintain that, or to get it spinning in that direction, you actually have to give it energy, okay? So if we talk about rotational kinetic energy in general, okay? Rotational kinetic energy, the formula for that was, it was equal to 1 half, let's talk about kinetic energy first. That'll make more sense. You guys are familiar with this 1 half mv squared? Well, rotational kinetic energy is 1 half rotational equivalent of mass. It wants to resist, right? That mass wants to resist the motion, okay? So that I value, moment of inertia, and then instead of v, we got to have a rotational component also, so we're going to get an omega squared. But you see how they're almost identical, right? It's just we have a rotational version of our mass and a rotational version of our speed, okay, or our velocity. So this, if we talk about this in terms of torque, one thing that I'm giving you guys right now is torque and rotational components. And when you talk about torque and rotational components, it was actually I alpha, okay? So this is actually really close to that already, okay? If you square a velocity, so a velocity squared, meters squared over second squared would be v squared, right? Acceleration is basically meters over second squared, so it's pretty close, right? But check this out, for rotational stuff, you've got omega, right, is going to be in radians per second, and alpha is going to be in radians per second squared. So if you squared this guy, you get radians squared over second squared. You're basically almost there. So it turns out that torque and rotational kinetic energy are really, really closely related. Okay, if you squared this one, you'd almost get there. So here's the thing. If you have a rotating object, any object at all, the way that you get it to move is by exerting torque on it. That's how you get it to rotate. So how do you get a kinetic energy, rotational kinetic energy? You got to use a torque to get it moving, okay? So when you guys did that race down a ramp, which hopefully you did, okay, you're going to find out that different objects, even disks, right, like these two, they have different I values. So even their moment of inertia changes, but why is that? Well, because of how torque acts on this thing. So if this thing is rolling down a ramp, right, it's not sliding down a ramp, it's actually rotating as it goes down a ramp. It never stops touching and moving, right, rolling as it goes down that ramp. So if it's not sliding at all, if it's only rotating, then all of this, really, you're getting a torque. Gravity is acting like a torque to make that little bit of mass here actually fall, right? It's pivoting about a center. So how it's acting, each little bit of mass in there is essentially acting with a torque. So it's like this. That edge of that wheel is like this little bit of mass, right? Except for we have masses all the way around that wheel. So let me get a couple of these and you can see what I'm talking about. Let me get 2 or 3 of these together. And here we go. So I've got a couple of these now. Get them set on here. So each one of these things just looks like a ball on a stick to begin with, because it is, right? But if you set them up in a certain way, you can actually see that that actually starts to look, get them at the same center point, the same radius here, right? That starts to look like the arc of a wheel, right? So what a wheel is it's actually a bunch of these things acting together as one. Okay, so every wheel is actually just a mixture of all these things, right? So each little tiny bit of mass for that piece or that piece or that piece, right? A wheel is just an addition of all of those things around, right? And you can imagine it takes a lot of torque to get this thing to lift it up, and gravity exerts a lot of torque to let it fall. So that's what gravity is doing on a wheel, okay? So a wheel that is not solid, that is hollow, kind of like this one, only has the mass mostly around the edge, you really just have a ball and a stick, right, all the way at the edge. So you get maximum torque off of this thing. You get a ton of torque that it takes to actually move this wheel around because that mass is farther out. Remember, with the torque, the radius, the radial distance away from the center to the edge matters. So the farther out it is, the more torque it's going to take, and the more kinetic energy it's going to take, rotational energy it's going to take to get it moving, okay? So these guys, if they're all in the end, it takes a lot of torque, and so a lot of rotational kinetic energy, or it takes energy, right, a lot of energy to get it moving in the first place. So if this thing is a wheel, in fact, right, and it's spinning around an axis, let me see if I can actually get this thing to set up so it'll actually look like a wheel, maybe, here, maybe, possibly. Can I do it? I don't know. Actually, it would have been smart if I put a hub in there. Maybe do that right now. Okay, so I got a hub here. Put them all together in here so it actually looks like a wheel, right? So now these things are going to act like an actual wheel. All right, so there you go. So there's basically a wheel, right? It's essentially just mostly empty space with the mass on the outside edge. And it takes all the torque, right, is acting way far out at a distance, okay? So you get a high torque out here. There's nothing in here, okay? There's basically nothing in here. Imagine these rods have no mass. So most of this is going to just take a mass at a distance away from the pivot point, and it's going to try and rotate it about that spot, right? So it's going to take a lot more energy to get this thing moving. So if you have this thing trying to roll down a ramp, well, gravity is actually just taking and acting on each thing like a pivot. It's going to make that fall, and when it does, it brings this one up, and it's going to make that one fall and bring this one up and move it around and so forth and so on, right? So to get it to go like that, it has to take a lot of torque to get it to move. So most of the potential energy actually gets wasted, essentially, in just getting this thing to spin up. If you have something like this, a solid disc, like this coaster, well, you don't just have a hollow space in between, okay? So you've actually got like masses that are essentially all the way down the length of this thing. So you have mass on top of mass on top of mass on the way down. So your torque, right, that it takes to get this thing moving is sort of an average torque. It's not just the torque at the end of this stick, right, up here with the purple one, but it's the average of all the torques in here. And so it actually gets to be less of a torque value for something that's solid. So it actually takes less torque to get this thing moving because a lot of the mass is towards the middle, not very far out from the center of the radius, right? Some of it's closer into the center radius, the center pivot point, than other parts. So it actually ends up with a lower torque. And that's why you get different I values for things. So it takes a different amount of torque to get something moving. The more mass on the edge of it, the more energy it will take to actually get it to rotate. And it will actually sap that energy away from the potential, or instead of using kinetic to just let it slide down the slope, it's going to take most of it and put it into making it roll. So if you did the race, you should have found that your hollow objects tended to lose that race. They lost the race because they took more torque to get them moving, and they ended up with more kinetic energy, rotational kinetic energy, as they went down the slope. The larger their radius, the more that's true. Okay? So, with that all being said, let's take a look at problem number